Hello, and welcome to our presentation for Autonomous Path Following and Obstacle Avoidance with MBOT Tunio. Here's what we will be covering for today. The goal of this project was to mimic how autonomous vehicles behave in city traffic. We used the MBOT Tunio and programmed it using Python on the CyberPy platform. The robot performs three main tasks, which are number 1, following a white line, number 2, detecting and reacting to traffic signs like red, green, and yellow, and finally, number 3, avoiding obstacles either by drifting or turning around. Overall, the robot navigated successfully and performed all the tasks reliably across multiple tests. Okay, so the project was inspired by real-world traffic system and autonomous driving technology. Our main challenge was to make the robot respond intelligently in real time using the basic sensors. To achieve this, we combined rule-based logic with sensor fusion in Python, allowing the robot to act appropriately based on what it detects. We started by reviewing mBlox sample projects such as KP line follow and obstacle avoidance. These helped us understand P-control and ultrasonic sensing. However, these lacked more complex behavior chaining, and we also studied platforms like LEGO Mindstorm or VEX Robotics. While they offer a good modular navigation, they often handle one behavior at a time, and they don't support time-based or multi-condition logic, which we need to focus on in our system. Let's move on to the system architecture. So architecture is monolithic and it's event-driven. So when the user presses the button B, it triggers the follow white path function. From there, the robot runs a continuous loop that handles line following, sign detection, and obstacle avoidance one at a time based on the priority. Our robot uses quad RGB sensors array to detect the white line and traffic signs in red, green, and yellow. It also has an ultrasonic sensor V2 that detects the objects that are closer than 7 centimeters. These two sensors will work together to help the robot make decisions in real time. Here's a look at the actual hardware. So on the left over here, you can see the ultrasonic sensors, and on the right, we have highlighted the 4 RGB sensors, R1, R2, L1, and L2, which are used for detecting both the line and the colored markers. To better explain how the robot behaves, we have created a flowchart of the entire behavior logic. This helps visualize how it moves from one action to the next depending on what it detects. The flowchart shows how the robot decides what to do based on what it senses. So, the main loop continuously checks for 3 things. Number 1, whether the white line is detected. Number 2, whether a traffic sign is seen. And number 3, whether an obstacle is in the way. If it sees a red sign, it stops. If it sees green after that, it resumes. A yellow sign triggers slowdown, and 2 greens in a row bring it back to full speed. When the robot detects an obstacle, it checks both sides. If one is clear, it drifts around. If both are blocked, it either turns or performs a full U-turn. The joystick can be used at any time to pause the robot's behavior safely. This system ensures that the robot acts logically based on its surrounding. Moving on to the methodology.
And now we talk about the methodologies of our algorithm. The first one is by following logic. The MBOT2 continuously reads lateral offset using the getOffsetTrack function to adjust wheel power accordingly. In more detail, the offset from getOffsetTrack function tells us how far the robot has ripped. We multiply it by the proportional gain Kp, which determines how strongly to correct for that rip. The left wheel power will be equal to the pace power minus the Kp multiplied by the offset, and the right wheel power will be equal to the pace power plus Kp multiplied by the offset, and then we multiply it by -1. Next is the traffic handling. When the robot detects the green card, it will resume normal operation if the robot is currently stopped by the red card. If the robot was not affected by the red or yellow card before, there will be an override function that makes the robot go straight. If the robot detects yellow card, it will slow down and start the timer. After that, if there are two rings appear, it will get back to its normal speed. Else it will be back to normal speed after 5 seconds. If the robot detects red card, it will stop immediately and start counting. If there is no ring appear after, it will make a U-turn after 10 seconds. Else it will be back to normal speed after see a ring card. Next, we have the LED and sound feedback for air reaction. There will be a green LED and upbeat tone if the robot detected green. A yellow LED and a mid-tone beep will appear if the robot detects yellow, and a red LED and low beat tone if the robot stops immediately on red side or there is obstacle detection. Next, we have the obstacle avoidance. For this, we use the Ultra Sensor 2, which is in front of the robot. We set the threshold distance is within 7 centimeters. So every time the robot detects an obstacle in front of it within 7 centimeters, it will activate the obstacle avoidance. We prevent false positive through delay and rechecking. In more detail, this is the flowchart of obstacle avoidance function. When the ultrasonic sensor reaches an obstacle within 7 centimeters, the robot pauses for 1 second to look for the red card underneath. If no red card is found, it turns left and then right to see whether the obstacle fully blocks the path. If partially blocked, it drifts around the obstacle and resumes live following. Else, if fully blocked, it executes a U-turn to go back around and avoid the obstacle. Next is the T-junction obstacle handling with red. If the obstacle is detected within 7 centimeters, the robot will stop for 1 second to check for the red color signal. If red is detected, it will form a turn to take another available path. Here are the results. The robot really good at white light following and obstacle avoidance. For traffic light reaction, the first challenge is ring passing. Every time it sees ring, it avoids as an effort to follow the white line. So our solution was to use an override function that makes the robot go straight as an effort to pass the ring when it detects the ring card. And it partially worked. The other challenge was obstacle coverage detection. Due to the hardware limitation, the ultrasonic sensor 2 cannot detect the coverage of the obstacle. After a while, we found a solution, which is we need to make the robot to go both sides to check for the coverage, and it worked perfectly. Now it's time for demo.
Hello and welcome to our demo of autonomous path following and obstacle avoidance with M-Boat Neo 2. First, we start with white line following. Using proportional control, the robot keeps itself centered on the path. It continuously adjusts its wheels for smooth, precise tracking. Moving on to obstacle avoidance. When the path is completely blocked, it halts and pivots 180 degrees. This guarantees that it can find a clear route every time. Now, partial obstacle, right drift. For a partially blocked path, it veers right around the obstacle, then it realigns to the line without losing momentum. Next on is partial obstacle, left drift. Similarly, it can drift left if that side is clear. The adaptive logic picks the optimal detour in real time. Next on is T-junction handling with red sign. At a red marker before a T-junction, it comes to a safe stop. Once clear, it selects and enters the correct branch. Next on, traffic sign handling, green sign. A green sign shows zero delay in its line tracking behavior. Next is red followed by green. It stops reliably on red and holds position. On green, it instantly accelerates back into motion. Now, if red persists for 10 seconds, After stopping at red, it counts down 10 seconds. Then it executes a precise 180-degree turnaround. Next on is on yellow sign slow down. A yellow marker triggers 5 seconds of slow mode. This ensures safe navigation through caution zones. Finally is yellow followed by 2 green signs. It slows down for yellow, then on the first green it keeps slow, on the second green it returns to full cruising power. That concludes our autonomous behavior demo. Thank you for watching the Embolt 2 Neo in action.
This is the map we used to test the robot. Thank you for watching.